All right, so in this video, we're going to be looking at complex numbers. Now, this is a fairly extensive treatment of complex numbers. We're going to start with the very basics, and then we're going to work all the way up to working with complex numbers in polar form. So this may be one of those things where you want to watch it in pieces. We don't usually introduce complex numbers all at once like this in algebra class. We'll do some of these more basic things, and then we'll circle back around to them after we have learned other things like polar coordinates. So let us continue. So complex numbers are built of two components, a real part and imaginary part. And so we're going to start with pure imaginary numbers. Now, imaginary numbers are defined essentially in terms of a negative under the square root. In fact, the number I is basically just the square root of -1, or sometimes it'll be defined as I squared is equal to -1. Basically, it means the same thing. If we have -4 under the square root, we can separate out the negative and the 4, and then take the square root of the 4 and bring that outside the square root, and then leave just the negative sign under the radical. So this would still be an imaginary number, but it would be essentially 2i. It would be a multiplier, a real multiplier of an imaginary number. So we have this notation that we use for the letter I for representing any square root that involves a negative number under the radical. Essentially, this I stands in for the square root of -1, and any other pieces that are under there, we pull outside the radical so that we can represent our number just as this 2i expression. Now, sometimes in other disciplines, you'll see other characters used. Sometimes, like in electrical engineering, you may see a J because I is used for current, which is also very common. And so the rules don't really change. It's just the notation may change a little bit. But we're going to use I because that stands for imaginary, and that's what we use in mathematics. Now, as I mentioned, because I is equal to the square root of -1, if you square both sides of the equation, you also get this property that I squared is equal to -1. And so that is something else that we're going to rely on as we start working with numbers that involve I and numbers that involve powers of I. Now, one way of thinking about complex numbers is that they don't really make a lot of sense in terms of like the real world. What is the square root of -1? And well, it's not really anything. That's why it's imaginary. So sometimes I find that it's best to encourage students to just think of them as it's a rule. It turns out that this rule, these relationships, actually work super well in certain contexts. So they're extremely useful, which is why we keep using them. If the imaginary numbers didn't have any function, if they didn't do anything, this would be just a clever thing that somebody wrote about in some obscure paper someplace, and nobody would be learning it. It would be just like, some properties of prime numbers that you only learn because they only work in like cryptography or something. You wouldn't be learning them in high school or community college unless you really needed to know them for things that you need to do in life. So particularly if you're going on to becoming an engineer, complex numbers turn out to be extremely important in a subject like differential equations. But again, they're not real. And so sometimes it's just useful to kind of get used to them by just thinking of them, okay, this is an expression, there's this notation, there are these rules that apply, and just go with the rules. And I found, like, again, I tried to overthink these too much. But just if you work with them, it's like, okay, there's a rule and I'm going to follow the rule and it works. So don't philosophize too much about them. So we're going to look at some examples of just rewriting our imaginary numbers where we have a negative under our square root. We're going to try rewriting these and simplifying them in terms of I. And then we're going to do some basic operations. So if I have a square root of, say, negative 18, then the first thing I can do is I can just pull out the -1 as a multiplier, because I know this is, I'm going to be able to represent this as I. And then I can simplify my 18, the square root of 18, just as I would normally. I can factor that as 9 and 2. The square root of 9 is 3. And the square root of 2 doesn't simplify. That's just square root of 2. And then the square root of -1, I can rewrite as I. And I is on the outside of the square root. Sometimes you'll see this written as 3i times the square root of 2 in order to emphasize the fact that the I is not actually under the radical. Normally, the I goes last. But again, sometimes we will move it around, particularly in print, just to make it really clear that this is actually not under the radical, it's outside the radical. Now, when I add two complex numbers together, I essentially add them in the same way that I would add numbers that are like, they have x's on them. I'm going to treat I like a variable, and I'm going to add like terms. So if I add 2x to 3x, I add the 2 and the 3, and I get 5x. And I'm going to do the same thing with 2i and 3i. I'm going to treat these like terms. I'm going to add the coefficients, 2 plus 3, and I'm going to get 5i. Now, we talked about I squared being equal to -1. So if I want to simplify the expression I cubed, then I'm going to separate this into I squared times I. I squared, according to my definition, is -1. And so I cubed turns out to just be -I. For I to the 4th, I'm going to do basically the same thing. I have one I squared times another I squared. I replace those with my definition, -1 times -1, that's 1. So I is the square root of -1, and then I squared is -1, and I cubed is -I, and then I to the 4th is 1. And then we cycle back around. So if I had I to the 5th, for instance, that would be I to the 4th, which is 1 times I, which is be I. And I continue this 4-level cycle as I go through. I, -1, I, 1. And it repeats. Now, we can use this fact in order to simplify expressions that are much larger. So for instance, I to the 17th is I to the 16th times I to the 16th is I to the 4th to the 4th. And since I to the 4th is 1, 1 to the 4th is also 1, I just simplify I to the 17th as I. Similarly, if I'm doing the 95th power, I can pull out 94 of them, any even number, times I. And then if this is even, I divide this by 2, and then I get 2 times 47 is 94. So I know I squared is -1. -1 to an odd power is still -1. And then my odd I left over gives me -I. So if you know that it's divisible by 4, you can use the I to the 4th as 1 factor. But if you don't know for sure that it's divisible by 4, you can just take out, divide this even part by 2, and then use the -1. And if it turns out to be divisible by 4, this exponent here will be even, and then a -1 to an even power would be 1. You'll get the same answer. Now, what if I want to multiply imaginary numbers together? Well, again, I'm going to treat it kind of like I'm multiplying polynomials. How would I multiply 3x by 4x? Well, I would multiply the coefficients, and then I would multiply the x's, and I would get 12x squared. Well, I'm going to do the same thing here. I'm going to multiply 3 by 4 and get 12, and then I'm going to multiply I by I and get I squared. But we know that I squared is -1, and therefore I'm going to get this simplified to -12. Now, some basic problem solving tips. Again, if you feel like in dealing with imaginary numbers is confusing because you don't know what the square root of -1 really is, again, think about it as rules, and we're dealing with them just like we're dealing with x. It is a variable that has an unknown value, and just follow the same rules that you would use. The only extra layer here is that unlike with an x, we're not going to replace x squared with -1, but here we will. When adding imaginary numbers, you add them just like you would like terms, add the coefficients. This will be true when we expand to complex numbers where we have both real and imaginary parts. Again, add like terms together. When multiplying imaginary numbers, just multiply them like you would with variables. But then you have to deal with the powers of I as one additional step. When reducing powers of I, if it's even, again, just divide the exponent by 2 and then replace the I squared with -1. And then you don't even need to know if it divides by 4. If the exponent is odd, then you end up with factoring out an I and then use the even power. And if it's already even, again, just use, separate it into I squared to some power, and then apply the -1 to get the simplification. And then finally, make sure that your final answer has no power of I greater than 1. So I, -1, -I, 1. But none of those have powers, just I. So if you have I squared or I cubed or anything like that left in your problem, you need to simplify it, keep going until you just have a constant or I left over. Now, complex numbers are basically a combination of real and imaginary components. So a plus bi is standard form. The I is, of course, the square root of -1. And so we're essentially adding a real number to an imaginary number. Often when we're referring to complex numbers, we replace the x variable with a z just to kind of remind ourselves that we're dealing with imaginary variables. So that's like a visual indicator. This isn't real. But it doesn't really change the behavior of the problem. You can use x if you want, but sometimes x is used for the real component and y is used for the imaginary component. And so this is just a notation that means that we're not confusing parts of the complex number with the whole complex number. Now, we have some operations on complex numbers that we need to talk about. So the real part of z is the notation we use when we're referring to just the part of the complex number that doesn't have the I on it. And imaginary part of z, so mz, is the coefficient of the I part. So the real part of z in this form would be a, the thing that doesn't have the I on it. And the imaginary part of z would be the thing that's multiplying I, but not the I itself, just the thing multiplying I. So if I was looking at like 3x plus 4, then, or sorry, 3 plus 4i, then the imaginary part of z would be 3 plus 4i. This would be 3, and this part would be 4. So 3 plus 4i. Not the I, just the 4. Now, the most common way that we encounter complex numbers is obtaining them from the quadratic equation. So recall that we have a quadratic equation solved for 0, and the a, b, and c come from the coefficients in our original problem. We'll get complex numbers from this if this piece under the square root turns out to be negative. So as an example, if I'm trying to solve the equation x squared plus x plus 1, this can't be factored. So I can use the quadratic formula to find it. When I use something like this, x squared plus 3x plus 1, I'll end up with a positive value under the square root. But in this case, I'm not going to end up with a positive value under the square root. So when I plug in my numbers, 1 is b, here's my b squared, 4 times 1 times 1 divided by 2 times 1. And then I end up with the square root of -3. So I'm going to rewrite this as the square root of 3 times I under the I is not under the radical. And then I can split this into two fractions, 1/2 plus and minus the square root of 3 over 2I. So this would be a complex number. It has a real part and an imaginary part. So again, if I'm looking for the real part of this number, that would be 1/2. And actually, there should be a negative sign out here that I dropped. This should be a -1/2. And the complex part would be, the imaginary part would be the square root of 3 over 2, but not the I. When you ask for imaginary part of z, you just put the coefficient, not the I. Now, the complex conjugate of a complex number is when you flip the sign of the complex part. So typically when you solve quadratic problems and you get complex solutions, you get a complex number and its conjugate as solutions. So 1/2 plus square root of 3 over 2I, and then also 1/2 minus square root of 3 over 2I would be solutions. Although these should both be negative if we're talking about that previous example. Now, one of the consequences of dealing with imaginary numbers is that we can make an extension for the fundamental theorem of algebra and saying that any polynomial with real coefficients will have an even number of complex roots. And we can further extend that even to any polynomial with complex coefficients will have n number of roots, where n is the total number of degrees, real or complex roots. If the coefficients are real, you'll have to have an even number of complex roots because they'll have to come in conjugate pairs. If you have complex coefficients, then that's not required, but you'll still get the same number of roots that you have the highest degree in your polynomial. Now, we want to perform basic operations on complex numbers as well as operations just on imaginary numbers that we did earlier. So when we perform operations on complex numbers, again, basically think of it like adding or even multiplying binomials with an x in them instead of an I. We're going to do everything with like terms. So if I add 3 minus 4i to 2 plus 6i, I'm going to add the 3 and the 2, and then I'm going to add the -4 and the 6, and I'm going to get 3 and 2 is 5, and -4 and 6 is 2i. Exactly like we would if we were adding 3 minus 4x and 2 plus 6x. And if I'm subtracting, the only thing I have to remember to do is distribute that minus sign and then add like terms. So 3 minus 2 would be 1, and -4 minus 6 would be -10i. Likewise, if I'm multiplying, then I'm going to have to treat them like binomials, which means I need to FOIL. So if I multiply 3 minus 4i times 2 plus 6i, 3 times 2 is 6, 3 times 6i is 18i, -4i times 2 is -8i, and -4 times I times 6i is -24i squared. Great, I can add my two middle terms, but I can't leave the I squared here. This isn't an X. I squared is -1, and so I have to make one more simplification step, which is to replace I squared with -1. That will make this into plus 24, and then I can, as a real number, and then I can add that to the 6. Again, I should not have any powers in my final answer where I is raised to a power other than 1. I can have an I, but no I squareds or cubes or whatever. Now, when we're dealing with division, we have to actually get the complex numbers out of the denominator in order to separate them into real and imaginary parts. And so the way that we're going to do this is we're going to multiply our denominator by its complex conjugate. And if I multiply the denominator by that, I have to multiply the numerator by that. And so I'm going to multiply this problem by 2 minus 3i over 2 minus 3i. Now, what that's going to do is essentially I'm going to create a difference of squares in the denominator. And when I do the multiplication, the middle terms that contain I only are going to cancel out. And so 2 times 2 is going to give me 4. 3i times minus 3i is minus 9i squared. But I squared is minus 1. So minus 9 times minus 1 is going to give me plus 9. And then I can just add these together and get 13. Now, because it's just a single term in the denominator, I can split my fraction into 2 pieces. And my real and imaginary parts are now going to come from my numerator. So I distribute my 4. 4 times 2 is 8. 4 times minus 3i is minus 12i. And then when my denominator is combined, I can split these into 8 over 13 and 12 over 13i. And so again, my real and my imaginary parts can be separated. This method of eliminating imaginary numbers in the denominator is very similar to the way we would rationalize expressions containing square roots. And the reason for that is simply because I is a square root. It is the square root of -1. And so the process that we use here and the process that we use here are basically the same thing. Now, once we have our imaginary numbers, our complex numbers, we actually want to think about how we would like sort of visualize them, how would we represent them. And so the way that we represent complex numbers is not on a straight line for real, as we would for real numbers. Instead, we treat them essentially like they're 2 components. The real part would go on the horizontal line, and the imaginary part would go on the vertical line like a y value. And so we can plot points that way. So for instance, in the complex plane, which is what we refer to this as, this point right here, 1 and 1i, would be essentially the point 1 plus I. Now, if we go over here, this point over here in this corner, we would have -1 in the real part and 1i in the vertical component. So that would be -1 plus I. Down here, -1 in the real part, but also -I or -1i in the complex, the imaginary component. So that would be -1 minus I. And then over here in the 4th quadrant, this would be positive real part 1, but negative real part -1 or minus I. So that would be 1 minus I. Now, this representation in the plane is actually how we're then going to be able to represent these eventually in polar coordinates and apply trigonometry stuff to them. So let's look at some examples. Again, state the real and imaginary parts for the following numbers. So here, the real part of this number is C. The imaginary part is just D. Again, this is just stressing when you're asked for the imaginary part of a complex number, you only give the coefficient of I. You don't say I in reporting the imaginary part. Here, the real part is 3. The imaginary part is -4. Here, the real part is 5. The imaginary part is 0 because there is no plus I on this number. And when you have pure imaginary numbers, the real part is 0. And the imaginary part is, again, just the coefficient of I. Give the real and imaginary solutions to the quadratic equation, real and imaginary parts of the solutions. So again, we apply the quadratic formula, and then we get square root of -23 from all of our algebra. We pull out the negative sign as an I, and then we can split our fraction into 1/4 plus or minus the square root of 23 over 4i. The real part is 1/4, and the imaginary part, we have two solutions, plus and minus the square root of 23/4. And again, that's a typo. That I should not be there. Give the complex conjugate of the following examples. The complex conjugate of z equals 4 minus 6i would be 4 plus 6i. For z equals 5, well, there's no imaginary part, so it's just 5. So 5 plus 0i and 5 minus 0i is exactly the same thing. And for z equals I, that would just become minus I. For the equation x to the 4th plus 3x cubed plus 6x squared plus x minus 4, how many roots does this polynomial have? Since the highest term is degree 4, this is a 4th degree polynomial, so it has to have 4 roots. Now, this is either going to have 4 real roots, 2 complex roots, and 2 real roots, or it could have 4 imaginary roots, but the roots will have to come in pairs. Here we have an example adding or subtracting the following complex numbers. So if I add 2 plus 4i to negative 7 plus 3i, I'm going to add the corresponding components. 2 and minus 7 is negative 5, and 4 and 3 is 7, so negative 5 plus 7i. If we subtract them, 2 minus a negative 7 is 9, and 4 minus a 3 would be 1i. Multiply and divide the following complex numbers. So if I multiply them, I'm just going to FOIL. So 1 times 3 is going to be 3. 1 times negative 4i is negative 4i. I times 3 is positive 3i. And then I times negative 4i is negative 4i squared. Negative 4i squared, the I squared gets replaced with negative 1. I can add my middle terms to get negative I. And then once this becomes a positive 4, I can add that to the 3 and get 7 minus I. And I didn't actually do the division on this handout. Now, some tips. When dealing with complex numbers, there are some strategies that you can use. If you are having trouble getting around your head exactly what complex numbers are, again, follow the rules. This basically treat them like variables, and eventually you'll feel better about it. Remember to move complex numbers from the denominator using the complex conjugate before attempting to simplify further. And then don't forget to replace I squared with negative 1. Your answers should not have any i's raised to powers in them. And when you're asked for the imaginary part of z, again, remember, don't report the I, just the coefficient. Now, if we're moving into polar and exponential form, we want to think about a couple of relationships between coordinates in polar form versus rectangular coordinates. So if I have a point in the xy plane, then I can measure the distance from the origin to that point, which essentially is the radius of a circle going through that spot. The radius is basically the square root of a squared plus b squared. And we can do the same thing for a point in the plane. 3 plus 4i, again, another typo, would be 3 squared plus 4 squared would give me 5 as my radius if this was 4i. Now, the notation for that magnitude of z, essentially what we would say is the length of z in the complex plane, is given in these absolute value bars. The length is always positive, but this is not just like make all the components positive. This is find that distance formula, do that square root of a squared plus b squared. Now, if I want to use polar form, I need to find the angle that is pointing at. And so again, I use this formula from dealing with theta in polar coordinates. It's the y component over the x component. Our complex part, our imaginary part, is the y component in the complex plane, and the x component is the real part. So this would be the inverse tangent of b over a. Again, this would give us values that are in the first and fourth quadrants and not the second and third quadrants. So you may need to add 180 degrees or pi radians in order to get you over to that half of the graph. So again, we'll look at an example. 3 plus 4i. The angle we get is not a nice one. So we'll represent it as approximately 0.93 radians or 53.1 degrees. This is in the first quadrant, so the inverse tangent is going to give us that value. So we don't have to add pi or 180 degrees in this case. However, if this was -3 plus 4i, we would have gotten a value in the fourth quadrant. But that point, -3 plus 4i, would have been in the second quadrant. So then we would have had to add pi radians, or again, if we're in degree form, 180 degrees to get into the appropriate quadrant, because the inverse tangent would not have given us a value in the second quadrant. It would have given us a value in the fourth quadrant. Sometimes this angle is sometimes referred to as the argument of z. And so you'll see that notation in some cases. Now, to get polar form, we essentially use those same radius and trig function transformations, where we think of t as our theta value, our cosine t is x, and our sine t is y. And we can double check these values. If we have 5 times the cosine of our radiant angle, we get, again, we rounded, so we get about 2.99, and our old value was 3. And if we do 5 times the sine, again, rounded, we do get about 4. So the difference here is just a rounding error. If we had carried more decimal places, we would have gotten even closer to this exact value. Now, in this handout, in some cases, I have rounded values to be decimals. If you are doing problems on your own, you may need to carry more decimal places than I have carried here. I've reduced them just for the sake of convenience, not because there's any reason why you should only have 2 decimal places. These are transcendental numbers. They're irrational. They have lots of decimal places, and the more that you carry, the more accurate your approximations will be. Now, there is a relationship where we can represent complex numbers in exponential form that is related to the Euler equation, where cosine t plus I sine t is e to the it. And then we multiply by the radius in order to get the length correct, because this cosine t plus I sine t expression only has a length of 1. So we can represent this exponential form of this complex number as 5, which was the radius we calculated, and e to the 0.93 approximately I, or the inverse tangent of 4 over 3. So let's consider multiplying 2 complex numbers in exponential form. So remember how this works. We would multiply the coefficients, but when you're multiplying 2 numbers with the same base, you add the exponents. So we can verify our solution by doing this both by converting to traditional rectangular form, a plus bi form, and then performing the operation, or we can do the operation with complex form and then look at the answer afterwards. So in this case, we would say 2 2 times 3 is 6, and 0.4 and 0.6 is e to the I, so that's a multiplier of 1. Now, if we were to put these back in rectangular coordinates, we would first convert each one. So 2 is our radius, and 0.4 is our angle. So 2 times cosine of 0.4 in radians, plus 2 times I, sine of 0.4, again in radians, would give me approximately 1.94 plus 0.779i. And then I do the same thing for e for the second term. This is my radius of 3, and my angle is 0.6 in radians. And I would get this approximately, again, rounded to 2 decimal places. And then I can multiply by foiling. Don't forget to replace I squared with -1, and we end up with this expression. But 6 times e to the I, if 6 is my radius and 1 is my angle, I can get this value directly by just using Euler's formula. Again, the difference, if there's any in this case, is just a rounding error because I only used 2 decimal places and not more. If we had carried an extra digit, then we would have gotten a more accurate answer. Now, we can also represent, because we're in polar form, we can represent this calculation in polar form. So multiplying 2 complex numbers, we would multiply the 2 radii together, and then the real part would be times the cosine of the sum of the 2 angles, and then I times the sine of the sum of the 2 angles. We can likewise do division much more easily in polar form than we can in Cartesian coordinates. So if I'm dividing these, I just subtract the exponents of the exponential. And I divide the coefficients. So 6 divided by 2 is 3, and pi minus pi over 2 is pi over 2. And if I want to convert this now to Cartesian coordinates, then I would just get 3i. Whereas on the other hand, if I were to try to do this simplification in Cartesian coordinates, then I would have to do the conversions and then multiply by the complex conjugate and then do a whole bunch of foiling and simplifying in order to get this answer. And so there is a formula we can do division with. Again, we will divide the 2 radii, and then the complex answer will be the cosine in the real part of the difference between the 2 angles, the 2 arguments, and I sine of the difference between the 2 arguments. Now, one of the really useful properties of dealing with polar coordinate or with complex numbers in polar form is when we need to raise complex numbers to a power, or when we want to find a root for a complex number. So like the square root or a cube root of a complex number. So suppose that I want to raise the number 1 plus I to the 6th power. So one way I can do this is to literally FOIL everything out and get that answer the long way. Another way, though, is I can represent this as an exponential form. Then I'm just multiplying the angle in the exponent, and then raising the root to that power as well. So let's walk through the comparison. So here, 1 plus 6i, I need to essentially FOIL everything out. If I use the binomial formula, then I get the coefficients from doing combinations. But again, you can get these by just literally doing all the foiling. Again, you can't distribute the 6 directly through the parentheses. It doesn't work. But what we end up with when we simplify all these powers of I is that we end up with this expression, and we add the real parts and they all cancel, and in this particular example, and the complex parts leave us with -8i. Now, how can we get that from exponential form? Well, we're going to look at our 1 plus I. So our radius is 1 squared plus 1 squared under the radical, which is the square root of 2. And the inverse tangent, the angle that we're going to get from this, is pi over 4, because it's the inverse tangent of 1. So our 1 plus I is represented as the square root of 2e to the pi over 4i. And then to raise that to the 6th power, we raise that whole exponential to the 6th power. We take our radius to the 6th power. Well, this is the square root of 2, so that's 2 to the 1/2. 1/2 times 6 is 3, so this is 2 cubed, which is 8. And here, we're going to multiply pi over 4 by 6. That gives us 3 pi over 2. 3 pi over 2 is the angle pointing downward along the imaginary axis. So e to the negative 3 pi over 2i, as you plug it into your trig functions, turns out to just be minus 1i. Sine of square of 3 pi over 2 is just minus 1. And that has an I on the outside, so you end up with negative 8i. So a lot less work than FOILing out 1 plus I times 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 1 plus I. So our general rule is that if I'm raising to a complex number to the n power, if I know I can represent it in exponential form, then it's the radius to that power and then cosine of n times the angle plus I sine of n times that angle. Now, roots work very similarly. So, for instance, the square root is a 1/2 exponent and the cube root is a 1/3 exponent. And so we can actually use this in order to get our roots. So consider the equation x to the 5th is equal to 1. Well, we know that there's a real solution where 1 is a solution. But what about the other 4 complex solutions? It has to have 5 answers according to our fundamental theorem of algebra. So how do we reduce this? So we're going to rewrite 1 as a complex number, 1 plus 0i, and we're going to get the angle, which turns out to be 0. But that's just going to get us the 1. So what are other ways that we can get 1 with different angles? Well, we come back around the circle, right? Every time we go through 2 pi. So there are actually other angles that will give us 1 as a real number. So those would be things like 2 pi, 4 pi, 6 pi, and 8 pi. And that will give us 5 angles that will give us the same real value of, if I put that into the exponent of my e, my complex exponential, I'm still going to get the same answer. But if I redo each of these in my formula, if I divide 2 pi by 5 and put that into my Euler's formula, I'm going to get another value for the root. And if I put in 4 pi to the 1/5, again, that's just another expression for 1, divide by 1/5, and I'm going to get another value for the 5th root. And if I do 6 pi over 5, I'm going to get another 1. And if I do 8 pi over 5, I'm going to get another 1. And notice that we have complex conjugates here. So this is 0.3090 plus 0.9511i, and here is 0.390 minus 0.9511i. Again, these are, I'm writing these out as decimal places just so that we can evaluate these crazy expressions and get them into something where we can more easily interpret the values. But same thing, here is negative 0.8090 plus 0.5878i, and here same real part, but flip the sign of the complex part. So these two are complex conjugates of each other, and these two are complex conjugates of each other, which is what we would have expected. Complex solutions have to come in pairs of complex conjugates. And so our general rule for the nth root of z is going to be r to the 1 over n. So that multiplier still has to go out front. But then we're going to take our angle plus various multiples of 2 pi divided by the root that we're using and apply that to Euler's formula the appropriate number of times. So if you're getting a fifth root, you need 5 solutions. So you would need 5 angles to do this until you start repeating. And then if you're doing a fourth root, you would need 4 total solutions and so forth. So we can look at some worked examples here. So 1 plus I, the magnitude of this, square root of 1 plus the square root of 1 is square root of 2. Inverse tangent is pi over 4. And so we could represent this in polar form this way or an exponential form this way. Now for B, the magnitude is 1 and the inverse tangent is 1 over 0 of the angle is the inverse tangent of 1 over 0. This is not defined. Tangent is not defined when the angle is pi over 2. So again, this is either going to be pi over 2 or 3 pi over 2, depending on whether this is plus or minus. This is minus I, so that's not positive pi over 2. That's going to be either negative pi over 2 or 3 pi over 2. For this one, this is a real number, so the angle is 0 because it's on the positive x-axis. And so the radius would be 3. If this was a negative number, we would use pi and a positive radius. And then for this one, again, we calculate our radius. 4 squared plus 9 squared gives me the square root of 13. Our inverse tangent is inverse tangent of -3 over -2. This is in the third quadrant though, so we're going to add pi to that radian value, and then we can express it either in polar form or in exponential form. And again, we're rounding just for simplicity. If I want to multiply these two numbers together, I can multiply the coefficients. So 2 times 3.4 is going to give me 6.8. And then I add the angles together. So I get negative 0.35. And so in polar form, this would be this. This is basically the same idea, but it's in polar form rather than exponential form. So I'm still going to multiply the coefficients together to get 12. And then I'm going to add the angles, which is going to give me 0.12 minus 0.7 is negative 0.58. And again, I'm leaving it in polar form because that's the way it was presented. And then if I want to divide, again, I divide my coefficients, so I get 2. I subtract my angles, I get 5 pi over 4, and thus my solution, again, in polar form, since I started in polar form. And for this one, again, follow the same rules. This is just in polar form already. So 6 over 3, I get 2. And then I subtract my angles, pi over 6, subtracting pi over 2, I get negative pi over 3. And again, I'm leaving it in polar form. For 2 minus I to the 5th, again, I could try to FOIL everything, but instead I'm going to calculate the angle and put it in polar form, so or exponential form. So square root of 5, and my angle, my argument is negative 0.464. This is in the fourth quadrant, so that is the right angle. And so then we're going to raise this to the 5th power. So the square root of 5 to the 5th is going to be 25 square root of 5. And 5 times this angle is going to be negative 2.32. And then we can, again, put it back into Cartesian form by applying our polar form and then evaluating it. So 5 square root of 5 times this cosine is the real part, and then 25 square root of 5 times the sign is the imaginary part. And again, rounding. If you have a calculator that can handle complex numbers and you actually do this a multiplication, you actually get 38 and 41i. But again, this is, if you carry more decimal places, then you'll get a more accurate solution. I do have another video on this channel where I actually show you how to do this multiplying in your calculator to check your results in the TI calculator. Now, it won't necessarily do all of these multiple roots for you, though, so you still have to know how to use these formulas. So if I want to simplify this fourth root of 2 minus I, again, I want to convert this to polar form. So I end up with the square root of 5, because this is 4 plus 1 under the radical. And then I did the previous example, I found this angle. Now, if I write this in exponential form and then I take the fourth root of everything, this is going to turn into the eighth root of 5 as my coefficient out front, so about 1.22. And if I divide this angle by 4, one solution is going to be this angle. And so if I write that in Cartesian form by evaluating my trig functions, I get this. But I still have 3 other solutions. So what I would have to do then to continue solving this is I would have to add 2 pi to my original angle and then divide by 4 and then reevaluate the new angle. And same thing, I would add 2 pi again, divide by 4, plug it into my polar form. That would get me solution number 3. And then solution number 4, I would add 2 pi again, divide by 4, and that would get me my fourth solution. If I did it one more time, I would get back to the same solution I had here. For problems involving multiplication and division, use whichever method you feel most comfortable with. The amount of work in terms of converting and then putting it back again, particularly if the powers are not large, may justify just using the binomial theorem. But that's both of them require a bit of practice in order to get used to. If you have to find 2 values, regardless of whether or not you use polar or exponential form, these values are the modulus and the complex number. The modulus, which is the magnitude of the complex number, that radius, and the angle or the argument. The modulus depends on the Cartesian form, the distance to the origin, the hypotenuse of a right triangle with sides A and B. If you have to use the exponential or polar form to solve for roots of unity or roots in general, that's roots of 1, you can't use the Cartesian form for this. You have to go to either the polar or the exponential form. For roots of unity, again, these are roots of 1. Remember, you're looking for the same number of roots as the power of the equation. So if you're trying to find the 6th root, you need 6 solutions. If you have the 5th root, you need to find 5 solutions. So you can find the first one, but then you have to keep adding pi over 2 pi to your angle, and then repeat the calculation until you get the required number of solutions. When calculating polar or exponential form, make sure that you check to see that your angle is in the correct quadrant. Add pi if it's not. When using the polar exponential form for multiplication, you may need to add or subtract multiples of 2 pi to keep the angle generally between negative pi and 2 pi for being sort of in the standard range of values. And then when doing roots of unity, again, calculating roots of 1, check your complex answers that they come in pairs of complex conjugates, because that is a requirement that they come in pairs of complex conjugates. So you can sometimes find calculation errors or typos if you're looking for those things.